you may be surprised a little bit because the title is extremely close to the title of last week. And there is a good reason for this because it's a kind of continuation. So therefore, I should apologize to those who read another title for the third lecture. But for many of you that I've been in touch in between, so I told that I will discuss topological features today and not phase transitions on fractals. But next week, we have another hour to discuss all this. So that's what I'm going to discuss today. As before, let me again acknowledge discussions and collaborations with a subgroup of people who have been involved in this talk, on the material that I will present today. So it's mostly a group in Rafael. I told you it's a kind of equivalent of the CEA, but in Israel. And especially most of the material that I will present is due to Eli Levy. The curves and all what you will see is to put to his credit. Okay, so let me, for those of you who were not, who could not come previously, let me just summarize what I did, what I said last week, because it's relevant for what I'm going to say today. In a previous lecture, we have discussed, I think I would say ad nauseum, the spectral properties of infinite Fibonacci chains, quasi-crystals, and we applied them successfully to finite systems. So there were questions whether it's possible or not. So all this, we dwell on those questions. Let me remember what is this working horse that we are using here. It's a quasi-periodic stack of dielectric layers of two types, two letters, A and B, and each of them is a dielectric system with its own width and its own refractive index. So this is the idea, and we arrange them according to the Fibonacci sequence that we generate using the concatenation rule, which means that a word at a given stage, step j, is built out of the two previous ones in the series. So if we start from B and A, you see that the next one is of length 2, and this is BA. The next one is of length 3, because it's the concatenation of this one and this one. It is ABA, ABA, etc. Like this, okay? We built a cavity, and this cavity, in this cavity there are modes that could exist in this dielectric cavity, and the spectrum, the mode spectrum of this system is fractal. So this is what I said. And what it means that if now you look at different Fibonacci chains which are scaled, different lengths, different number of words, of letters, then you see that the density of modes indeed has this self-similar type of structure. And if we look at the, so this is this self-similar structure, which means that if we scale this part by a given factor fixed, depends on Fibonacci, we get the same structure. If we scale this part again by the same factor, we get the same, so we have a self-similar spectrum. If we look at the integrated density of states, the integral of this, so we have this kind of devil staircase picture, and again, we have, if we zoom in, we get exactly the same structure. If we zoom in again, we get exactly the same structure, and eventually, as expected, we see some effects of finite size. Okay. So this integrated density of modes exhibits also log periodic oscillations, and this is what I presented last week. And we said that those log periodic oscillations, this structure, which is visible both theoretically, of course, and experimentally using this polariton experiment done at LPN Marcoussis, then those log periodic oscillations, we said, is the indisputable fingerprint of the underlying fractal structure of the spectrum, which means that having just, this is the this counting function, the integrated of the density of states as a function of energy, and just a power law, even with a non-trivial power, this is not enough to just decide that we have a fractal. You need also this part, which are those log periodic oscillations. This is essential to just say that this is a fractal. This is not something else. Okay, so all this we said. And we said something else, which was also rather relevant. We said that if we look at this Deville staircase, this integrated density of states, we could label the gaps, only the gaps here, those gaps, using two integers. So we can say that the integrated density of states at an energy that is inside the gap can be written that way, where tau is the golden mean. And those two integers, p and q, are topologically invariant. They are Chaire numbers, and they are independent of the potential strengths and the inhomogeneities that could happen on the chain, and so on and so forth. So again, they are really known, demonstrated mathematically as Chaire numbers, topological numbers. Okay. So this being said, what is the program for today is to investigate the topological properties of this Fibonacci chain, to discuss the nature and the origin of those Chaire numbers that we just saw, and to see how it's possible to obtain them from scattering theory. Okay, so that's what we'd like to do. And more precisely, so we mentioned that there are Chaire numbers to describe the gaps. So this is an outcome of this gap labeling theorem. But the natural question, especially today, that there is a lot of excitations around those topological numbers and so on, is there a relation with other occurrences of Chaire numbers, for instance, in the quantum Hall effect, topological insulators, graphene, you name them. And this is not so obvious, because in the previous cases, the cases that are listed here, topology arises from a given obvious, perhaps not always very obvious, associated Berry connection. I will discuss in a second what I mean by this. And this topology usually results from the existence of underlying magnetic fields, either magnetic field that you put from outside, like in the quantum Hall effect, or that you design with a lot of work and with a lot of patience and attention and a lot of design. And magnetic fields are Aharonov-Bohm fluxes or a specific Dirac structure, which is natural to have such that kind of topological invariance. But here, obviously, we don't have them. So before going further, I would like to remind you, not to remind you, to just set up a few definitions, a few basic things, which it's perhaps a little bit technical, but at least it gives some common background for topological issues. So the basic ingredients to talk about topology are the following. So first of all, so it's really extremely superficial. I mean, I don't expect you, I mean, those who are familiar with this, they will say it's obvious. Those who are not familiar with this would say, okay, I understood nothing, just, I could say Hebrew, Chinese, I don't know. Okay, so the idea, the base words are the following. You define first a non-trivial manifold. Non-trivial manifold is something that could be defined as a product of manifolds, for instance, a torus. It's a product of two manifolds. And over this, so it's kind of things that I discussed also in the first lecture, but again, you may not have been here in the first lectures, but, and now on this manifold, you define a structure. In the jargon, this structure is called the fiber bundle, okay, F, I call it F. So if you speak in a physical language, in fact, M is the physical space of your system, and F is the representation of a continuous symmetry group, which is carried by a field, by an order parameter, or you name it. Now, on this fiber bundle, you define a connection. Connection, for mathematics, the translation in physics is a potential, vector potential. Okay? And from this connection, you define a related curvature. In our language, a magnetic field. But again, it's much richer and much broader than this, but just this is the idea. And now, if you want to define systematically a possible topological invariance on this fiber bundle, you define what is called Chern classes. And those Chern classes are obtained through systematic expansion using what is called invariant polynomials. So this goes with the name of a theorem, a very well-known theorem that is associated to Chern and Weil. And such a polynomial can be expanded that way. And those, what appears here systematically, there is a way to do it, are Chern classes. Okay, so now again, I'm sure that it's split into people that are bored and to people that are say, I understand nothing. Okay, that's fair enough. Okay, now I take an example. I take the plane, two-dimensional plane, and I define on this plane an order parameter, which is this one. So here the fiber is just the complex numbers, and the Lie group associated to this is just U1, I mean, just complex numbers. And the connection one form is this circulation of the potential, vector potential. The curvature two form is just the magnetic field, okay, so which is related to A through this curl. The invariant polynomial in that case is very simple. It contains only one Chern class, and this Chern class can be written that way. And now the Chern number is the integral over the closed manifold of this Chern class, and this is always an integer. And this is called the Chern number. Okay, so the Chern number is the integral of over the Chern class. And this is nothing but the flux quantization condition that is known in a closed manifold. So all this is to set up few ideas, words, notations, and all this. If you want to know a little bit more about those very, very simple physical aspects of this, many years ago with Chiron, when people were not so busy with Chern numbers, we wrote a review on this for Les Ouches, so you can just look at it. All this is taken from this review. Okay, so another example, which is also extremely considered very often those days, is the example of free electrons in a 2D crystal and magnetic field, plus an applied perpendicular magnetic field. This is the so-called Harper problem. And here you can define also a non-trivial group of magnetic translations, which are generated by the momentum, generalized momentum in the x and y direction. And this group has this commutation law, where alpha here is the flux through the system in units of the normal flux quantum. And if you plot the spectrum, which is the energy as a function of this magnetic flux, you get the so-called Hofstadter butterfly, which is not only important, it's also beautiful. And if now you decide to read this picture using the Chern class or the Chern number description filter, then you obtain this not less nice picture, which is due to Osacci and Yossi Avron, and in which each phase here is in fact characterized by a given Chern number. So it's a way, it's a kind of generalization, not a kind, it's a generalization of this gap labeling theorem, in which in fact each of those gaps can be labeled by a Chern number. Okay, so I will not say much more on this because topological features of Harper and the related Aubry-André model have been extensively covered here, I mean Paris at large, for instance, in the lectures of Jean of last year and in many other places. So just to give you a taste of the background. Okay, so now what about our Fibonacci quasicrystals? Again, in the light of all what I said, is there a Berry connection and a corresponding curvature whose integral produces corresponding Chern numbers for this problem? And is it possible to define a non-trivial fiber bundle, such as the group of magnetic translations, such as in the Harper model? And is there a quantity that plays the role of a magnetic field? Here, there is no magnetic field in this problem. Okay? So that's the kind of question that we would be interested to answer. Okay, so now another thing that we know is that those topological features, as we saw for the Fibonacci chain, are obtained for the infinite system. They are bulk contributions, right? And we know from the Hall effect, from here also we will see, that in fact a way to measure those bulk number is to use finite size system and to use in fact edge states, modes, either transport through the system, so you need a finite size system. And here I would like to do the same, to see if there are, if those topological features manifest through some specific properties of edge modes or gap modes, this depends who is speaking, in the presence of boundaries. So, what I want to say is that under certain boundary conditions that I will detail later on, instead of observing this kind of spectrum that I just showed a few slides before, what we observe is something else, is this, where here you observe that there are, in fact, additional modes that show up here, and those are gap modes, okay? So this is, those modes, they always appear if now you consider a finite size system, okay? And I want to study those modes, and I claim that those modes will tell me about those bulk topological numbers, okay? So that's the idea. Okay, so those gap modes, they move through the gap. They move spectrally as a function of a given parameter, phi, that I will determine later. And in fact, here is typically the kind of picture that I want to show you and to explain to you, is that there is a parameter that when you look at such edge states, so this is the spectrum, and this is the same spectrum, but viewed as a function of this yet undetermined parameter phi, and you see that those modes, when you change phi, they move. They could enter the gap, go out of the gap, reappear here, and so on. And you see that they move differently in different gaps, and this is what I want to study. This is the idea that I want to convey. And this is very analogous to what, again, is extremely well studied those days, which is this idea that you have bands, and in between you have edge states that are moving as a function of a parameter, that here it's energy as a function of momentum, but here it's the same idea, except that now I have to define what is this parameter phi. So this is what I want to show, and this is analogous to what is already well known. Okay, so far so good? Okay, good, for me too. Okay, now in order to understand the existence and the nature of those edge states, which mean to implement the program that I just described, in fact, we need to discuss the different but equivalent ways to build a quasi-periodic chains. So there are four, which are well known since a long time, which are well documented everywhere. So I just wish to remind you those four equivalent ways to build a quasi-periodic chain. One is concatenation, we saw, substitution matrix, characteristic function, cut and project method. Okay. So concatenation is what I showed before. It's a way to build this chain by just putting together the result of the two previous runs. Remember the Fibonacci mills? Okay. So this is the way. This is concatenation. Now, by building a chain using this concatenation, you notice obviously that the length of the chain is necessarily a Fibonacci number. It cannot be different from this. And therefore, it is not possible to generate chains of arbitrary length. You can generate only chains like this. Okay. The second method is called the substitution matrix. It's very important. And the idea is the following. Consider a substitution which is acting on a given alphabet of here 2 letters. Okay? So 2 letters are A and B. And this substitution changes A into BA and B into A. Now, to such a substitution, we can associate a matrix a 2x2 matrix whose columns gives the number of letters A and B which occurs in the transform. So, for instance, here we get 1 and 1 because here we have 1A and 1B. Here we get 1 and 0 because we get just 1A but no B. Okay? So this is this matrix. And now by successive application of this transformation sigma, we generate a word of length a Fibonacci number. Again, this is constrained. We cannot generate length, a system of arbitrary lengths. And the words sigma to the power n of b converge to an infinite sequence, which is called sigma infinite of A or B. And this sequence is left invariant by sigma, which means a fixed point. Okay, simple. Okay, so this is a very important way to do this. We will go back to this in a moment. It's very important. Now there is a third way, which is called characteristic function. So this way, in fact, has a very long history. So again, you know, I don't put all the references and all the credit to all due person because there are many. So I guess that one of the first to promote this was Barry Simon, a mathematician. And second best, I think, or in the time, was Jean-Marc Luc from Saclay. And recently, in fact, there were a series of papers by around two people, Krauss and Oded Zilberberg, that used it in a very clever way in a series of papers. So the idea goes that way. You define a function, which is this function. And this function is the sign of this difference between two cosines, where tau is the golden mean. And this function, you see, so it's a function of n. Now for each value of n, it can take either value +1 or -1. If it is -1, you call it b. If it is +1, you call it a. Okay? And now like this, you generate a word, which is chi1, chi2, chi-n, a word of length n, whatever length you want. And this word will be translated into a series of a, b like this. And like this, you generate, in fact, a Fibonacci structure. So what is interesting here is that the length of the chain is whatever you want. Okay? It does not have to be a Fibonacci number. And there is an angle that shows up here, phi, which appears as a new and legitimate degree of freedom. And usually it is ignored. It is ignored for a given reason because it's irrelevant, which is a good reason to be ignored. And moreover, when it is not ignored, although it is known to be irrelevant, when it is not ignored, it is considered a nuisance. But not here. Here it will not be a nuisance. Okay? Okay, so that's the characteristic function. And then is the last method, the last approach, which is called the cut and project method, or mappings. And here I would like to take a little bit more time, because first of all, it will be important here. But just, I mean, okay, you know, sorry about my ignorance, but I really discovered the breadth of this field during the last few months. And in fact, this is an extremely active branch in math of tiling, not only in 1D, not only in 2D, not only in 3D, but in whatever dimensions. It's just fantastic field of mathematics, of tiling, of dynamical systems, of classical information theory. And in fact, so here I listed a very, very short subset of mathematicians, mostly, but sometimes physical mathematics people that are active in this or were at the origin of this field, just to show you that, in fact, it's a branch of math that is extremely active in France, that I think started mostly in France. I don't know if Michel will agree with me. Yeah, Yves Meyer and Mendes France and Alouche. Okay, so. And so it's really beautiful. It's fantastic. Just for, you know, if I could give you the taste to go and to see so what it is about, it's already something good for a good outcome of this talk. So anyway, this is a way to generate both periodic and quasi-periodic structures. It's not limited to this. And here I will give a very brief tutorial for practical implementation in 1D system. Okay, so what is the idea? Very briefly. You start from a 2D periodic lattice, this lattice of points, Z2, and then you draw a line, which is just a line with a given slope that I call B, and with an origin that is wherever you want. Okay, this is a constant. And now around this line, you draw two parallel lines so that you define a strip. Okay? Now this strip cannot be too wide, but you take it to be equal to this. And again, I don't want to enter into the details, but the details are important here. But here, just consider this case of. And then now you count the number of points that fall into this strip. So there are all the points that are in blue here, okay? And the third thing is that you project all those points on the line that we had initially in a direction that is perpendicular to this line, okay? So doing this, you generate a number of distances between neighboring projections, right? And now you give a letter, you put a letter to each of those distances. But the surprise is that like this, you generate only two possible distances. Not 3, not 4, not 25, just 2. Okay? So this is already not a trivial result. So you generate a structure, which is a structure made out of words, made out of 2 letters. Okay? And the letters are those distances. Okay. So now, depending if you have a rational slope, here, for instance, I took 2/3. If you have a rational slope, then what you generate is a periodic superlattice. So you generate a lattice with here this periodicity, which is 3. So this is the lattice that you generate, ABA, ABA, ABA. But again, 2 letters only. And if you take now an irrational slope, you generate a quasi-periodic structure. And this quasi-periodic structure, so here I took the golden mean. And this is our Fibonacci structure that we generate like this. So this is yet another way to generate a Fibonacci chain. Okay, good. And now I want to stress again that all the 4 previous methods are absolutely equivalent and allow to generate infinite quasi-periodic Fibonacci chains that are just the same. Okay? But they involve important and interesting differences. The first one is that substitution and concatenation generate fixed structures, the chains, which are chains of lengths given by a given Fibonacci number. It cannot be whatever you want, only this. Cut and project and characteristic function do not involve a constraint on the length. But more importantly, they allow for an additional degree of freedom, which is this phase phi, which appear in the characteristic function approach. So this was there. But then you would ask, what is the meaning of this strange phase phi in the cut and project approach? So what is the meaning of it? So I remind you where this phi showed up in the characteristic function. And as I said, this is usually an innocuous and thus ignored modulation phase for the infinite system. And for an infinite Fibonacci structure, it even has a value, this phase. It is equal to 3 pi divided by the golden mean. Okay? So that we can define, instead of just a phi, we can define a delta phi, which is difference with respect to the Fibonacci phase. Okay? Now, what is the equivalent of this in the cut and project method? So is it possible to give a meaning to the phase delta phi, this phase, within this picture? And it is possible. And the meaning of this is just a translation in the y direction. So which means that if you take this structure and you just pull it up or down along the y direction, in fact, what you generate is exactly what you have this. So which means that what we had the constant here is in fact just minus delta phi divided by 2 pi. So this delta phi has a very clear meaning in the cut and project description. Okay, so now we understand better what is this delta phi, at least in this picture. And I would like now to list some of the properties of these cut and project methods and this delta phi that we just discovered here. So first of all, each value of the phase delta phi accounts for an existing segment of the infinite Fibonacci chain. So this is not very surprising what I'm saying. I'm saying the following. Here, we generate a given Fibonacci chain. Now, if I take this chain and translate it somewhere, I generate another chain, segment. And this segment, if I look at the infinite chain, of course, I will find this segment somewhere. Okay? You're with me? Each step is boring, but at the end, that's the outcome that is not boring. So that's the idea, I think, no? This is the lobster technique, no? Trying to... Okay, now, delta phi is 2 pi periodic. And this delta phi corresponds to a translation along the chain, which means along this chain here, along the chain here, which is like of delta n, which means that each time that you move along the y direction, in fact, you make a translation along the chain. Okay? So I will show it now more precisely. First of all, so this is the way I describe it. So each time you start from, I'm not sure that I'm very clear here. So suppose that you have something like this. So this is this code that I have here. So this sequence of 6 letters is BAA, BAB. It's BAA. There are 2 A's here, BAB. Okay? And then if you change delta phi, you may have a given sweep between 2 letters, which means that you could go from this structure to that structure. And that structure is BAB, AAB. Okay? You cannot have BB in the Fibonacci chain. Okay? So you are with me? This is the idea of what is represented here. And now I would like to see how a change of phase delta phi is implemented along the chain. So this is a chain. This is this chain of 88 letters. And here I change delta phi along this axis. And you see that for each value of delta phi, I could either have a defect like this or not. This depends. Okay? You are with me? Yes? Don't be shy. You can say that you're not with me. Okay? Okay, so now there is periodicity, which means here, so here I erased all what is in between, but you see that if you move from 0 to 1, which means delta phi between 0 and 2 pi, this is the initial structure that we had. After this 2 pi, we get exactly the same. Okay? In between was something, but here you get exactly the same. So it's periodic. After 2 pi, you get exactly the same structure. Whatever is the length. Here it was 88, but it does not matter. Second, it is a translation, I said. So here, this is the initial sequence that we had. If you move to this value of delta phi, say, then you see that we had a translation by just 1 letter. So, okay, this is the whole structure was just translated along this direction. Okay? So here, what I'm saying now is that this structural, what I'm telling now is just structural. This structural degree of freedom generates local structural changes. And these changes have a meaning only for a finite length chain, not for the infinite chain. So this is the whole structure. So this is for 88 letters. This is the delta phi. And what you see is that this is the defect. You see that for a given value of delta phi, you can have only a single defect. You cannot have 2. It's extremely important, this. You cannot have only 1. So which means that if you draw a line here, either you catch a defect or none. But you cannot have 2 for the same value of delta phi. Which means that if you look at the event numbers as function of delta phi, you have those steps which are of unit 1. You cannot have 2. Okay? And now, if you look at different values of the neighboring values of delta phi, so once the defect will be here, but then the next defect will be here, so it looks a little bit erratic if you follow it as a function of delta phi. But if you look at the whole picture, you see that it is not really erratic. Okay? So here the lobster is working hard, I see. Okay, so now the question, is there a symmetry of the Fibonacci chain probed when scanning this phase over a period? What is the symmetry? So the symmetry is palindromicity. So palindromicity, what I'm saying is that by scanning the phase delta phi, I drive the chain through a palindromic cycle. So what is a palindrome? Palindrome is this. Okay, it's a symmetric structure that can be read both directions. Okay, so which means that this chain, when I'm changing delta phi, I go through values at which the chain is symmetric, is palindromic. Okay? So to remind you, first of all, is that Fibonacci chains that are generated using substitution or concatenations, the two bad ways that we had to generate it, in fact, they are almost palindromic, all of them. So if you look, for instance, the value n equals to 5, so except for those two, it's palindromic. So it's not really almost palindromic. But if you look at 8, it's the same. You look at 13, it's the same. So this is palindromic, and here there is a small part that is not, which means that an infinite Fibonacci chain contains arbitrarily long palindromic substructures. Okay? So this is also important. And alternatively, if we use the characteristic function or the Katten project to generate the chains, then we can also monitor delta phi and to consider chains of arbitrary lengths. So now what I define is a parameter that accounts for structural palindromicity. So this parameter just counts. So if it is 0, the way it is defined, if it is 0, we are palindromic. If it is non-zero, we are not palindromic. And now this is this parameter here as a function of delta phi. And you see that we have those steps, which means what I said, and there are two values at which we are palindromic. And those values, they depend on tau, which is the slope of the Katten project method, and the length n of the chain. But there are always two, no matter what. There are always two values at which the chain will be palindromic. So you take whatever chain you have, you scan delta phi through a period from minus pi to plus pi, and then you observe that there are two values at which you are palindromic, always. Okay? And the Fibonacci value is somewhere here. It's for delta phi is equal to 0 by definition. And there usually you are not palindromic. You're almost palindromic. Okay? Now, the deviation from palindromicity saturates here, you noticed, at a value. And this value, in fact, depends only on the Katten project slope, which means only on the type of quasi-periodic potential. For another one, it could saturate or not saturate. We will see it in a second. Here, in fact, this number depends on the occurrence of the AA doublet in the chain. And the AA doublet, you see that they saturate to this value that we will see in a second. Why? And 1 minus this gives just this. Okay? So this value of the saturation is something that depends only on the structure, on nothing else, not on coherence or whatever, just on the structure. Okay, so now the question, all what I said is structural properties of chains. Now question, are there spectral consequences on these structural properties? I remind you that I want to calculate Chaire numbers at the end of the day, at the end of the hour. Okay, the answer is no. There are no spectral consequences of this. In fact, it's almost no. Okay, so this is this almost that will make us busy for the rest of the talk. So, in fact, we have already calculated and measured the spectrum in details. This is what I said at the beginning. So this is the spectrum that we obtained. Remind you, those pictures, we obtained this gap labeling theorem and this, all those beautiful values, Chaire numbers, whatever, all what we said. And all those characteristics are independent of the phase delta phi. So let me show it to you. So this is this spectrum that we had before. So this is just this spectrum, or that one, it's not important. I take, so those are two gaps, two other gaps, etc. And now I change delta phi and look at the spectrum. And this is what I obtain. So indeed, the spectrum is independent of delta phi. So why are we here? Okay? So now the question is, this looks independent of delta phi, but we obtained the gap labeling theorem, also those Chaire numbers, using, in fact, the substitution matrix approach. So this is what I said last week, but I didn't show it. And so now I would like to show you a demonstration of the gap labeling theorem, at least what I call the whole calculation is not the whole calculation, because, but just something, the ingredients, basic ingredients that we need to understand that the gap labeling theorem is absolutely independent of this delta phi. It has nothing to do with delta phi. Okay? So let's look at this. First of all, the gap labeling theorem is based on this substitution matrix method. So I remind you what I just said 10 minutes ago, that substitution matrix goes like this. You have this transformation that can be described using this matrix, and we generate all this. Okay? Now, we can define densities, dA and dB, of letters in the fixed point infinite Fibonacci chains. And in fact, those densities, which mean the ratio of letters that are A or B, and they are given by the components of the positive eigenvector, this one, of the matrix M that I wrote before, with the highest eigenvalue normalized so that the density of A and B is equal to 1. Okay? So it's a little bit of, they are very simple mathematics, in fact, but just to show you the ingredients. So for the Fibonacci chains, the eigenvalues of the matrix M, which was this 1, 1, 1, 0, are the solutions of this. There are two eigenvalues, the golden mean and the inverse golden mean, and the eigenvector that corresponds to this is this. So which means that in the Fibonacci chain, the density of A letters is given by this, and the density of B letters is given by this, and this adds to 1. Okay? But for the gap labeling theorem, in fact, we need only one more ingredient, which is, in fact, the substitution matrix for 2 letters, which means those substitutions. Not only 1 letter, but also 2 letters. So this is the matrix. It's 3 by 3 and not 4 by 4 because BB is forbidden. Okay? Don't take it as a political opinion. So this is the substitution matrix. And now for the Fibonacci chain, this matrix has eigenvalues which are solutions of this, which means the highest eigenvalue is again a golden mean, and the corresponding normalized vector is this one. This gives the density of AA, of AB, and of BA. By the way, you note that the frequency of AA is given by this, and for our chain, it's 23.7%, which is what I said before. Okay? So when I claim that the saturation value depends only on the Katten project slope, and it depends only on the kind of quasi-crystal, this is why I claim this. So this depends only on tau. Okay, very good. So now we can phrase at least the poor man's version of the gap labeling theorem. For an Hamiltonian that is determined by a substitution on a finite alphabet, the values of the integrated density of states, the counting function on the spectral gaps in 0, 0, 1, belongs to something that is called that way. Michel could tell us what it means. It's module. Generated by, but this something is generated, this is what is important, by the components of the normalized eigenvectors V1 and V2 that I just wrote, which correspond to maximal eigenvalue tau of M and M2. This is what you need, not more, no less. Okay? Only this. When you apply it on the Fibonacci chain, you get this expression, which is this. Okay? So again, what I wanted to convey here is that there is absolutely no need of whatever delta phi, structure, whatever. Everything is just contained here. You give me, for this substitution matrix, the one-word and two-word matrices. You calculate the eigenvectors, the eigenvalue, and you have this gap labeling theorem. So which means that those two integers, p and q, which are Chaire numbers, they are obviously independent of delta phi because we obtained it from something that has absolutely nothing to do with delta phi. Okay? So far, so good. There will be an occasion very soon to wake up for those people that went. Okay. So the substitution matrix approach does not involve what I said, the structural modulation phase delta phi, and which is, as we saw, irrelevant for the infinite chain. There is an important consequence, is that the counting function in the spectral gaps is independent of delta phi. Now I have even more important consequence. What I claim is that the counting function and the density of states over the whole spectrum, not only in the gaps, is also independent of this phase delta phi. So nothing depends on delta phi. This is what I said at the beginning, right? So in order to show it, I want to use this scattering formalism and something that is called the Crunch-Finger formula. So this is an intermezzo for people that follow. So this, I mean, if you were lost before, now it's reset. It's completely new. For 2 or 3 slides, you can just say, look, I learned something which has nothing to do with this damn Fibonacci and all this. Okay, so let's go on. It's basic on one leg description of scattering. Scattering formalism, first of all, offers a general and elegant framework in order to investigate spectral properties and transport properties of systems. If it is transport properties, it is better known as the Landauer approach, and so on. And here I will consider this kind of formalism only for 1D systems. Okay? So consider a quantum system or a wave system with a potential, which is defined with respect to a free part somewhere outside, and you enclose it in a black box, blue box. Okay, and you probe it using scattering waves. So you have incoming and outgoing scattering waves, incoming, outgoing, outgoing. And with obvious notations, the scattering matrix is unitary and can relate outgoing waves to incoming waves. Okay, so this is simple. Again, I'm saying only simple things. This matrix can be diagonalized. It is unitary. It can be diagonalized with two phases, phi 1 and phi 2. And we can define the total phase shift, which is just the sum of those two phase shifts divided by 2 for convenience. Okay? So assume now that the scattering potential decreases fast enough, as I said. And now I put this system that I have, my real physical system, in a huge box of size L. L is whatever you want. It's absolutely irrelevant parameter. Okay? And you apply periodic boundary conditions to this box. Again, it has nothing to do with the true system, the boundary conditions on the system. It has to be on this hypothetical virtual box. So applying periodic boundary condition, which is this, you get just a set of conditions. And those algebraic equations, you can write it as a spectral condition on the S matrix and K that you are looking for. Okay? So this is equivalent to this spectral condition. Right? Now, this spectral condition allows you to get a relation between the total phase shift and the possible wave vectors inside your structure. And this is the relation. You see that the possible wave vectors, they're related to the undisturbed part and the phase shift at a given solution. When you solve this, you get the spectrum. Okay? So what is nice about this is that this relation, which is extremely simple, leads immediately to an expression for the change of density of states. So this is the density of states of your system, and this is density of states for the free system. And the change of density of states can be related only to the derivative of the total phase shift, or if you prefer to write it in terms of the S matrix in a Bayes invariant system, it is given by this. So this is a beautiful formula which gives you the spectrum of a finite system, whatever is inside, by just measuring the S matrix. Okay? So there is also a nice short review. No, not nice, but there is a short review about this. And so this formula is in fact an example of a general formula that is called the Krein-Biermann, who were mathematicians. Schwinger was physicist, the Schwinger relation, which says that if you have a given regular function of an Hamiltonian, then the trace of this guy can be related always to the S matrix that is related to this. It's an extremely useful equation. Okay? So you don't need to solve boundary conditions. Just look at the S matrix. Okay, this is the end of the intermezzo. So now, for those who went... okay, so now... Fibonacci. So this Fibonacci chain that we had, we can embed it between two free spaces. And there we have this transmission coefficient, transmission phase, reflection phase, and we know that the density of states is just given by this kind of formula. And this generates just this spectrum. This is the way we calculated, in fact, the spectrum of the Fibonacci chain. And this total phase shift here, which is the phase shift associated to this transmission phase, is independent of the modulation phase. So therefore, the spectrum does not depend on delta phi. But, however, now we can consider, because we know that delta phi measures the deviation from palindromicity, we can look at the difference between two different scattering configurations. One where we probe it from here, and one where we probe it from there. Okay? So here we probe something that has to do with, not with the spectrum perhaps, but with the difference between the two. So in which case, we have the same transmission phase here, but here we have a reflection coefficient whose phase depends whether we are coming this way or this way, whether we are palindromic or not. So here I call alpha this chiral angle that measures the difference between the two. And if I plot now this chiral angle as a function of delta phi, which is this plot, you remember that we saw in a second, then what I obtain is this, is that this alpha as a function of delta phi, so this is plotted for two different wave vectors, you see that this alpha indeed depends on delta phi. So this is alpha for a given gap somewhere, this is alpha for another gap, and you see that in fact this now chiral angle depends on delta phi. Okay. Now, on which physical quantity do we see a delta phi dependence? Okay, we could say on boundary edge states. There is no choice because we know that scattering states are independent of delta phi. This is all what I said so far. So now how to build boundary edge states and how to relate them to the scattering formalism. So creating edge modes. So edge modes, as we know, they show up in most finite superlattices at gap frequencies that depend on boundary conditions. Okay, now it's not scattering. They are just edge states, modes. Those boundary states can be due to closed boundary condition. For instance, if I put a mirror at the end of my chain or somewhere, they can be due to interface modes, to defect modes, whatever you want, but all edge modes have the same origin and they're all of topological nature, always. So now I choose to work with a mirror, which means that I take my Fibonacci and I put a mirror here. By putting a mirror, I generate gap modes, necessarily. Okay? But now what I would like to do is to build an equivalent structure to this. And if here I put a mirror, you see that this is equivalent to this structure, where I put my Fibonacci and just the opposite of it. Because when I'm going back, what I look is this anti-Fibonacci. Okay? So this is the same as this. But the interest of this is that this I can study as a scattering system. This is an open system. This is not. Okay? So for this, there is a scattering matrix and everything. Okay? You're with me? Yeah? So here is the catch. I mean, this is here that I caught you. I caught you. I did not, but okay. So now, the edge states that I generate here, I have the edge states here in this structure. So this is an artificial palindrome. It has nothing to do with the palindromic structure of each of them. Of course, it's artificial. It will remain artificial and palindromic. So this structure displays additional modes in the band gaps. The gap locations of this structure or that structure remain unchanged with respect to the original structure. And the frequencies at which the gap modes show up depend on the structural modulation phase delta phi. So here is a plot of it. So this is the structure. This is the mode, the distribution of mode, density of modes of this structure. So you see that there are additional modes here for two different values of delta phi. So they are placed one here. In another gap, they are different. But you see that the structure of the gaps remain absolutely the same. It's absolutely unchanged. Now, if you look at it as a function of phi, so this was the structure that we had before. And this is the structure of this. So now you don't see anything. So this is the structure now of those additional modes, how they vary when I change delta phi. So you see that they move through the gaps. Okay, and now those gap modes, you see that they move through the gaps in the discrete staircase way, which depends on the contrast of the Fibonacci letters, which mean the refractive index and the length. And you see that for a very slow contrast, they move slowly. For a very high contrast, they move very erratically like this. And this kind of behavior, by the way, could not be achieved using in the Harper or Aubry-André model because they are continuous models. And now look at the dwell time, the time that those modes are inside the gap as a function of the gap. So first of all, it is periodic with the modulation phase, with a period that depends on the gap. So this is this plot is the same as this plot. So this is the spectrum. You see gaps here. And in different gaps, you see that there are modes, those modes that travel through the gap. Okay? And you see that the way the period that they travel with depends on the gap. And it depends if it is this gap. So you see that there are very, very many travels. This one, there is only 2, etc. So this is this picture that I represent, okay? So now, what is the relation to the palindromic cycle? So here, those are those modes which are represented here, okay? So each mode here, as a function of delta phi, is for a given gap, okay? So this one is for that gap. No, sorry, this one is for that gap, this one is for that gap, and here is the palindromic cycle. Now, if you reset the origin, what you see is that this is our palindromic cycle, and you see that at palindromic values, there are absolutely no gap modes in the structure. So each time that the structure is palindromic, there are no edge states in the system. It's free of edge states, but in between, you see that there are different edge states that move through the gaps, okay? And they move more or less rapidly. It could happen also that some of the modes disappear, although we are at maximum palindromicity, or some of the modes could disappear at another value, okay? Now, the nice plot, I think this is the most important plot, there is a relation between where we are in the gaps and those modes. So remember that each gap is characterized by two Chaire numbers, P and Q. So for each Q, so here it's Q equal to 1. For Q equal to 1, you see that this mode traverses with a period 1. For minus 1, you see that it traverses with the same period, but in the opposite direction, which means that instead of going like this, it goes like that. So it keeps the sign of this Chaire number, and it keeps also the value of it. So you see that for minus 2, we go like this, with half the period of this, but for plus 2, we go with the same period, but in the opposite direction. Okay? So this is a way to just measure those Chaire numbers. So the Chaire numbers describe the behavior of the topological edge states in the gaps when changing the structural phase angle delta phi, meaning while moving away from palindromicity. Okay? So, I have 2 minutes. The relation between the Chaire numbers for each gap and the scattering matrix now. So I remind you that if we have this structure, we found this chiral angle that depends on the structural phase, you remember. And this angle describes the difference between the reflection phase in that direction, in that framework, and the reflection phase in that setup, okay, when I attack here or when I have an incident way here. Now, this is what I showed you previously, that this chiral angle alpha depends on delta phi, and now you see that, in fact, it depends, the way that it goes through the gap, it depends where we are, in which gap. So it depends on the Chaire numbers. And you see that, again, at palindromicity, there are no such states. Okay? So what we saw is that this alpha, this chiral angle, defines the spectral deviation from palindromicity. First of all, it depends on the Chaire number in the gap. Second, it depends on the frequency in the gap. It's a spectral quantity. Third, it depends on the structural phase angle, delta phi. And finally, it does not saturate, unlike structural palindromicity, which what I mean by this is that here we have the saturation, but this angle does not saturate. Okay, it can go up to pi. Okay, so it does not depend on the fact that we have a tau or another irrational. Okay, so now what I plot here is again the same. So this is delta phi. So this is our Chaire numbers, our integrated density of states. Now what is plotted here for each value of q, so this is q is equal to -1, what is plotted here is delta phi, k, and the false color plot is alpha. So you see that alpha is equal to 0 for delta phi is equal to 0, then goes to a maximum at pi, and then goes to 0, at pi over 2, then goes to 0, and so on. If the Chaire number is equal to 2, you see that the periodicity is twice. If the Chaire number is equal to 4, you see the periodicity is again doubled. And if it is 6, so you have something like this. So this means that the Chaire number q of a gap and this chiral phase are related. How they are related? So they are related in that way. So if you look at this, in fact, this alpha depends on the structural phase, but it can be written in terms of the reflection phase here minus the reflection phase here. Now, if the two systems are identical, this is minus this, so this is twice a given reflected angle. So this is not the transmitted angle. This transmitted angle does not depend on delta phi. It is only alpha is just twice this. And in fact, the Chaire number is nothing but the winding number of this reflected phase shift, which is associated to the structural phase. So this is what we saw before. Okay? Chaire number is just a winding number, which is what we expect from a good topological number. Okay, so it's time to conclude. This is the first conclusion. The Chaire number Q is half the winding number of the spectral deviation from palindromicity, this alpha here, which is associated to the structural phase. Okay. Let me summarize all what I said. I said that the topological structure of finite size quasi-periodic chains is induced by the palindromic symmetry of the system. This is, in fact, the non-trivial fiber bundle of the system. Again, there are no magnetic field here. There is a direct relation between the scattering data, here this chiral reflection phase, and the Chaire number. So by measuring this, you can measure directly the Chaire numbers. And the cut and project method and the scattering theory give a simple way to calculate or to measure. This is a question for numerous colleagues here, the Chaire numbers. Okay? Now, there are things that I did not discuss, but which are also quite interesting, is that looking at a structure like this, we can describe it as an effective Fabry-Perot system, and it is very systematic and very simple design of topological mirrors, so I call it a topological mirror. And there is a very simple resonance condition that allows to calculate the position of the gap modes, and this is this resonance condition. So you suppose that here you have, in fact, a Fabry-Perot cavity, effective one, even if the distance is 0, even if they are just close one to the other. And this Fabry-Perot length is related to not the chiral angle, but the sum of the two. And once you have the Fabry-Perot condition, which means that this is equal to an integer times half the wavelength, then you get a mode in the gap. And you see, so here it's a calculation of this condition and the numerics that we had, and it fits absolutely perfectly. Okay, so this is a very simple way to get these gap modes, this Fabry-Perot condition. We can have a hand on the spatial structure of those topological modes. So they are, first of all, located at the boundary, which is here for this artificial palindrome. It's in the middle. If not, it is where is the mirror. They are exponentially localized. And in fact, the localization length depends on the frequency and therefore depends on the Chaire number. And here is an example. I mean, okay, you should be able to see it. It's not very obvious. So here are two edge modes, which are at different frequencies and, in fact, are differently localized. So this is what I wanted just to say. This is an interesting system to look at the Casimir effect between such topological mirrors. It is also interesting to understand the topological origin of fractional charge. Fractional charge is something that is extremely well known in other systems. One is polyacetylene, which is described by this SSH Su-Schrieffer-Higger model. It's also a very interesting system to study the quantum anomaly for relativistic fermions, as put up by Jackie and Rebbe many years ago. So in fact, I have a nice intermezzo on this, but I gave up for this time. But I hesitated for a long time. And then you can relate it also to more general classes of topological invariants that goes with the name of the Atiyah-Zinger index theorem that Michel knows extremely well. And what is interesting is that those topological invariants are known to be able to be described using scattering theory. So there are a lot of papers in high energy physics on this. Thank you very much for your attention.